digging holes in Oklahoma and modeling groundwater at the Umatilla Indian Reservation. Welcome to Geology Talk, our monthly gathering of geology enthusiasts brought to you by the Geological Society of the Oregon Country. We are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We have ample support from the Portland State Department of Geology and the Beverly Vogt Scholarship Fund. My name is Paul Edison Lam. I'm Communications Director of the Geological Society, and joined today, hopefully, by Andrew Dunning of Better Geology. We also have Kate Eli from the Confederated Tribes of the Umatilla Indian Reservation, who will be talking about groundwater. Andrew, you've been traveling. Where have you been?
Where haven't I been is a better question. 2 weeks ago, I was in Oklahoma doing a paleoseismic investigation on the Mears Fault, which is the largest active fault in Oklahoma, which is capable of generating magnitude 7 and greater earthquakes, which are big anywhere, but Oklahoma is one of those places that we don't generally associate with major earthquakes. And so understanding the earthquake history is really important at this site for understanding both for hazard and also for, the frequency of earthquakes tells you something about how the crust is building up strain effectively. So Ashley Strige and myself, Nick Roberts, Obina Oziko, Rudd Moe, and Christy, I don't remember her last name, all from PSU, flew out to Oklahoma and dug a big hole in the ground. This is actually the third time this particular site that we did has been excavated for earthquake history research, but this is the biggest one. Let me pull it up in Google Earth. So here's Oklahoma. It's a state in the central United States. And the Mears Fault is the only pink line, or actually line of any color inside the state. And this line is from the Geological Survey's Quaternary Faults and Folds database, which is a database of all the active or thought to be active faults in the United States, including Alaska and Hawaii. And this is the only one that shows up in there. And on this revision of the data set, it's actually changed a little bit since then, but it is 54 kilometers long, which is roughly, I believe, the length of the Ridgecrest earthquake rupture. So that's a large fault, and it's not certain right now on whether or not it ruptures all at once or in several sections. But Ashley's been working on this site near the tiny ranching town of Mears for about 10 years now. And in that time, she's done 2 trenches. The first time was re-excavating a trench that was actually done in the 1980s. And they went back to it, just sort of calibrate the data better and maybe get a little bit deeper and just get a better, clearer idea of what's going on out here. And it's located north of the Wichita Mountains, which is a part of Oklahoma I had no idea existed. Oklahoma does have some mountains. They may not be stratovolcanoes, but they are roughly 1,000-foot tall granite domes and pinnacles that sort of rise up suddenly out of the plains, as well as these sort of low hills here. These are called the Slick Hills. And this area is flanked really on both sides by very productive oil fields. You can see, I don't know if you can see all the white dots here in this area of the map. Those are all oil wells. They're all over the state. And the Mears Fault is a reactivation of a fault that was part of one of the times North America tried to split in half. This is the North American failed rift. So these rocks date to about 500 to 600 million years ago for the granites, and the early Permian for these rocks, which are limestones. So that's 290 to 300 and something million years ago. And so we dug our trench right here, right along the fault, about in the middle of its length. Let me get rid of the line showing the scarp. There. And so it shows up very well on the landscape and aerial photography. It goes right down the middle of this view here. Right there. Off into the sunset on both sides. So it's a beautiful structure. It expresses itself very well at the surface. And this site is really good for trenching because it's located in the base of a small drainage. Let's get some, yeah, this imagery has vegetation in it. So here's the fault. And in this little area, this creek, which starts here and continues out this way, has been laterally deflected. This fault moves laterally like this. It is left lateral. So an earthquake, this side goes this direction and the north side goes to the left, that direction. And over the lifespan of this creek, it's been offset by 400 meters, which is huge. That's the kind of stream offsets you get on the San Andreas Fault. But of course, we're in the middle of North America, nowhere near a plate boundary. So to have structures with this magnitude of offset is really cool and also really puzzling. But that's not what I'm here for. I was just helping out dig a big hole. So we did it in this drainage because the idea is after every earthquake, the exposure gets slowly buried. We assume there's a more or less constant influx of sediment over time into this little area. And that preserves the surface features and deformation that relate to each earthquake. The trench was done right in the middle of this site. I'll keep this open now. Now I'm going to go to some of my photographs. There we go. So we get into town and the first order of business is to go to Home Depot and get a whole bunch of stuff because we're not going to fly all of our shovels and buckets and whatever from Portland over there. We had to get a whole ton of stuff to prepare. We went through Oklahoma City, which is amazing, really cool town. Completely surprised me. I expected it to be pretty lame, but it's actually really neat. There's a great historic downtown district and a river walk, which I didn't expect to find. But eventually we made it down to the field site in the Wichita Mountains, and this is heading out to the site on our first morning. You can see the size of these big granite domes. It's just,
I guess we're
beautiful.
not. We're still seeing Google Earth.
Oh, I'm still paused. There we go.
Okay. Thanks, Diana.
Yeah.
Wow,
Home
that's
Depot,
beautiful.
yeah. Downtown Oklahoma City, lovely. Oklahoma City, lovely. There we go. There's the plains, the prairie, and the granite domes of the Wichita Mountains. We're digging this trench on private land. This is the Kimball Ranch, one of the largest cattle ranches in this portion of Oklahoma. And to get out there, it's just rangeland. It's just prairie. So we followed the tracks that the excavator made. We got to use a great big excavator for this project, which is a big improvement over the previous ones I worked on, where we did them either by hand or with a tiny little backhoe. So we followed this excavator all the way across the prairie. And got these sweeping views of the mountain range. It's still loading. This is a large, there we go. This beautiful, beautiful country. Weather was pretty pleasant the whole time I was there, except for a couple of days it was hot. And following the excavator, which goes anywhere it wants to go up to the field site. And here we are actually standing on the fault scarp. This is, there's a better one in a bit that has a better sense of scale. That's better. This is our whole crew, except for me, who's taking the picture. And at this site, this fault scarp is about 2 meters tall. So it's a good size feature. And it shows up really, really clearly. Because we're on bedrock here, it produces a nice sharp feature, which you can see all the way into the distance. Great teaching example for what a fault scarp is. And we get to the site ready to excavate, which of course the excavator does very well because that's its purpose. And here's Ashley in the hole looking for evidence of her previous trench. So every time we do a trench, we put nails in the wall to mark different features that we see. And she's here finding those nails from her previous trench. And we were very careful to make sure we kept as many of those as possible to be able to cross-reference with this time and our previous work. And this is our first view of the Mears Fault. You can see it here as this diagonal white line crossing through the middle of the frame. We can see this orange sort of soil conglomerate developed on top of this limestone conglomerate bedrock. And you see that down here on the down-thrown side of the fault. So that's that was our first sign of it. It was very exciting to see the fault. And of course, we had to keep digging the hole. This is as big as it got. It's a good sized hole. It took us a long time to clean it. So we have to scrape all the sides off because the excavator leaves all these smears of mud along the wall. And we need to get rid of that to be able to see the sediments and the strata behind it. So we took a group photo and headed down to the restaurant for the evening. And then we came back and the busy work began. So the sun is so intense out there, so we brought a little easy up so we can have some shade. We're walking around. This is the fault scarp just uphill. It's actually about 4 meters tall here. It's huge. It's all in bedrock. It looks like that from a distance. And here's the trench right across the middle of the fault. And here's the vault viewed again from a different location. Okay, so every morning we walked down to the site. Well, half of us walked down to the site. We only took one vehicle down, which was the pickup truck we rented. And we didn't take the other vehicle we had down just to reduce fire hazard, parking on all this dry prairie grass, which, you know, you get some beautiful views walking across the prairie just after sunrise. So that was really nice. Then the busy work began of cleaning all the sides. You see these smudges here. There's one here, or all these teeth drag marks in the floor of the trench. All of that had to go. We have to get rid of all of that. And this Oklahoma soil dries rock hard. So the first 2 days we had the trench open, we really had to hustle to get as much of that off as possible because it just turns to solid rock and you have to take a rock hammer and chip it off. Really, really rough, really brutal. But eventually we got all that done, and then we had to mark a grid on the walls of the trench. You see these white squares. That is a 1 meter by 1/2 of a meter grid. So that way, when we are mapping, you're effectively mapping the walls of the trench on paper. Then we can measure things easily and keep track of where things are. And this is Ashley right on the upthrown side of the fault. Oh yeah, so there's, in addition to the left lateral strike slip motion, there's also a vertical component, a reverse component. So the side Ashley is standing on moves up over the downthrown side of the fault, which you'll see in a bit. Some beautiful strata, good view of the scarp. Oh yeah, this is a good video. This has the vehicle in it for scale.
Andrew, we're coming right up on our 1 o'clock.
Oh yeah, okay, I'll speed this along then. There's your scarp, it's very large. Okay, here's some of the soils we found. There's this red, really, really deep red soil on top of this brown one. So we interpret that as this red soil being related to individual earthquake events because it projects down directly into the fault. So the fault generates an earthquake and it squeezes this red soil into a dome, which we call a positive flower structure. Then we use the camera to photo document the whole walls of the trench, which allows us to go to put those into the computer and build a 3D model. I had to leave, unfortunately, early, so I didn't get to see those. That took a lot of work to get that all prepared. And the fault zone here, This is actually a secondary fracture off the side of the fault, and the main plane is over here on this side. But after all that, this was my last time in the trench. I had to leave on Saturday because I had to fly on Sunday to Detroit for a different function. But this is the fault here, and this is that positive flower structure, this orangish, reddish bulge here. Really beautiful textbook quality exposures. I was hoping to find something close up of the fault plane. This is more colluvial wedge post-earthquake deposit, and this is that bedrock. It shows up beautifully in any photograph of it. It's a really good site. I had a lot of fun. Stank that I had to leave early, but I'll be working on it here in town, I'm sure, processing a lot of that data. That's all I got. It was a lot of fun.
That's wonderful, Andrew. Thank you so much. And we're looking forward to, more of a report on what the underlying tectonics of that is in the history of the earthquakes there. Kate, if you could introduce yourself and share your screen when you're ready to do so.
Well, good afternoon. It's wonderful to be here and to share our work over the past 10, 20 years for the Confederated Tribes of the Umatilla Indian Reservation. The picture we see before us is a photograph from Vicki McConnell. This was 20 years ago when she worked for the Department of Geology and Mineral Industries. And we have the Umatilla Basin in the foreground and the Columbia River basalt rocks in the background there, a beautiful display of rocks. And this presentation is about the groundwater conceptual model that we've been developing the past, like I said, 10, 20 years. It all begins basically with the geology, stratigraphy, and defining a geologic framework. So here I am. I work for the Water Resources Program in the Department of Natural Resources. And basically, our goal is to ensure that there's adequate, clean, cold water to produce the first foods for use by the tribal and non-tribal community members, and to ensure that there's water for economic development of the reservation. Now, first foods, you ask? Well, first foods are water, salmon, big game, roots, and berries. And according to the tribal creation story, the animals and plants held council to address the coming of people. They will not have any food to eat. And the salmon was the first to present himself to the people, followed by big game, roots, and then berries. The covenant was formed between the first foods and the people, where the first foods promised themselves to the people, and the people, in reciprocity, promised to care and to take care of the first foods for all time. All right, so now the first foods, they live at different elevations and in different ecosystems, and their requirements are vast and varied, and they have different ecosystem demands, environmental demands. And with water, that includes groundwater, surface water, springs, precipitation, and we need to consider climate change and global warming, basically, and climate change with precipitation and heat changes. So we're working to protect the first foods. Our department director developed a mission statement, and I need to read this for the first foods in our work at the Confederated Tribes. And that is to protect, to restore, and enhance the first foods, the water, salmon, deer, cows, and huckleberry for the perpetual cultural, economic, and sovereign benefit of the CCIR. We will accomplish this utilizing traditional ecological and cultural knowledge and science to inform population and habitat management goals and actions and natural resources policies and regulatory mechanisms. So, and our department is aligned around these first foods. I don't know, I can't see the entire screen in sharing mode here, but do you see the outline up above with introduction, background?
We see
Geologic.
first foods, water, salmon, big game, roots, and berries, and that's the text that we see on the screen.
Okay, well, there's actually a, my apologies. There's a menu up above that has introduction, background, geologic framework, hydrologic data, and new research. And that's the basic outline of patient. So now we're in the introduction. Okay, now you probably see the background aspect, right?
Yes, we do.
Okay, good. All right, so to ensure the health and vitality of first foods in respect of groundwater supplies and availability, we need to support some sort of sustainable way to manage resources for the future. And the easiest and most economical way to do that is to develop a computer model, a numerical transient state computer model to look at the effects of current groundwater pumping and water resources development into the future to anticipate what the impacts will be in groundwater availability and surface water flows. Groundwater moves considerably slower than surface water. Groundwater moves at tens feet per day, whereas surface water is measured in cubic feet per second. So we have, 80,000 times different in flow rates between groundwater and surface water. And so if you want to understand the effects of development on surface waters, you really need to go decades into the future to predict those impacts. So we are trying to build a computer model and taking these steps to do it. And it begins with quantifying and characterizing tribal water resources, collecting hydrologic data and monitoring conditions, building a conceptual model, which this talk is about. And then from that data and information, build a predictive computer model, validate it with the monitoring data and the data that is filled, simulate the hydrologic conditions, and then improve with this information, improve management strategies and policies and putting it all to practice. And this takes years to collect the data, monitor the data, and building a computer model. So we are right now developing the conceptual model with the idea of the computer model. Okay, so excuse me, what is a conceptual model? Well, basically it's bringing, information from the hydrologic system together. We have inflow, outflow, changes in storage in the diagram to the right. And it is basically showing how we think the system behaves. So in our study area, we have a set of data that for our conceptual model and ultimately to develop a groundwater budget, we pull together these data. We have precipitation, evapotranspiration, well use, groundwater pumping from municipal irrigation and domestic wells. We have spring flow, surface runoff, that's stream gauging data. And then we analyze the gauging data and separate it for how much groundwater inflow to streams takes place. And then we also used all this data to estimate the recharge to the basalt aquifers. Now, the recharge was estimated by the U.S. Geological Survey using their deep percolation model. And so we came up with a bulk value. And after pulling together this data and looking at this conceptual model, we realized, well, we needed a better understanding of the recharge mechanisms and the aquifer mixing between the shallow and deep aquifers. And that's the future research that I'll present here today. But so this is our basic data set. And the type of aquifers we have in the Umatilla Basin are shown in this illustration. We have, Umatilla River here in downtown Pendleton, and rocks of the Columbia River Basalt Group in the hillside here, and Blue Mountain in the background, and gravels deposited by the river here in this cross section. And then we have layered basalt, in the hillsides going down beneath the surface, this cross section. Okay, and the aquifers that most people use in the Umatilla River Basin comes from the basalts, and the aquifers, which are rock formations that store and transmit water to a well, occur in zones between basalt flows. So this is a very narrow band of area between the basalts that have the ability to store and transmit water. The basalt flows themselves are dense and hard and have very little pore space to none, and are incapable of transmitting water. So it's the zone between the basalt flows that are potential aquifers. Of the 300 so mapped basalt flows in the Columbia Basin, there's a handful of aquifers. Most of the interflow zones are not water bearing. Okay, and the illustration on the right is a typical salt flow with different cooling features, and it's this rubbly area between the flows that are the interflow zones here. Okay, so let's look at the basalts. Oh, let's look at our study area. Is the upper Umatilla River Basin, and we'll see an upcoming animation. But this is the Umatilla River Basin itself, with the Blue Mountains to the southeast and the Columbia River to the northwest. And the entire area is underlain by the Columbia River Basalt Group. That 300 or so flows we'll see comes across this area that you see in the left picture. It's eastern Washington and Oregon and western Idaho, 500,000 square miles of Columbia River Basalt Group. And last year in the field trip, we looked at basalt flows that flowed out to the Pacific Ocean from vents and fissures on the east side. We'll see those in the upcoming slide, but one basalt flow covers an area, like in this example, a huge amount of area. And for comparison, we have the eruptions from Hawaii and Iceland in this little inset here. So quite extensive. And in the study area, the Grand Ronde basalt occupies our entire area. So let's look at the fissure eruptions. These are cracks in the ground where magma pours out onto the surface. And we have layered basalt here and lava pouring out. And when it pours out, it's viscous, and we call it basalt flows. And when once it reaches the surface and cools, we still call it basalt flows. Sorry about that terminology. And here's an example of the fissure eruption along Hawaii fissure, recent eruption. And you can see the fountains are relatively mild compared to the 10,000 or so feet of fountains from the Columbia River basalt eruptions. The ballistic modeling predicted how high and how far it was necessary energy to produce the flows that wind up at the Pacific Ocean. So these are the interflow zones, potential aquifers in our study area. And here's a expanded view of the Columbia River basalt province that includes the Steens basalts and Oahe. And these are the fissures that produce the Columbia River basalt flows. Okay, interflow zones is where we have broken up rock that provide the storage and transmission of water through the rock formation, aquifers. And here we have layered basalt, which we see virtually little brecciated zones to provide any water. So, oops, excuse me. So distinguishing the basalts, is quite difficult in the field, and it requires cuttings and geochemical analysis. And when we analyze the data, titanium oxide and magnesium oxide are telltale signs of which of the flow units you are in. Grand Ronde basalt has titanium oxides less than 2.5, and Wanapum basalts have titanium concentrations greater than 2.5 weight%. So this is how we tell the difference between something that looks completely alike in the field. So here are the distinguishing units in that photograph we saw earlier, where we have the Grand Ronde basalt formation here and the Wanapum basalt formation above it. Mark Ferns and Vicki McConnell with the Oregon Department of Geology and Mineral Industries mapped the entire reach of the Umatilla River Basin and distinguished the units within each of the formations. The Grand Ronde basalt in our classic references refer to R2, N2, R1, N1, and those are polarity distinctions, normal and reverse polarity. And that's how those units were defined in the past. But with Mark and Vicki's work, we're able to, give them names and distinctions like Winter Water Unit and Sentinel Bluffs Unit within the Grand Ronde Formation. That was a major step in our understanding of the geology and developing our framework. It was fantastic work by those two. And we had a field trip, and we looked at the distinction between the Grand Ronde and basalt formation. And there's, in this picture, it's separated with a visible unit called the Vantage Horizon, which belongs to the Ellensburg Formation. It's a marker bed for us in the field. Grand Ronde below and Wanapum above. And then between the Sentinel Bluff and the Winter Water Unit, we have these spring sites coming forth, and they're not flowing out across and providing lots of water for springs at these interflow zones. And here's an example of interflow zones in the Johnson Creek watershed. This is not common in our region, which is semi-arid in much of it. So here's our animation now of our specific study area where we have the Columbia River and the Blue Mountains. And then we'll see the cities of Pendleton and Walla Walla, and in the north is the Tri-Cities area, and then the Umatilla Indian Reservation and the Umatilla National Forest. And we'll see the 89-mile length of Umatilla River and the Umatilla River Basin that we saw on the previous slide. And then our specific 913 square mile study area. And then we're going to rotate this and look at the land use in a block format. So here we have Google image, which we use a lot out here. And north is now to the upper left. And we have the Blue Mountains with the Forest Service and tribal lands. And then we have the, excuse me, I'm going to, this water. And we have the Columbia Plateau with, this is the South Reservation, North Reservation, City of Pendleton, irrigated land a little bit to the north and a little bit on South Reservation. The Umatilla River cutting across the Blue Mountains through the reservation. And this is a 3-time vertical exaggeration. It's 5,500 feet thick here. And I don't know, I can't see on my right side, but 10,000 feet to the right. All right. So with compression, faulting, and uplift, we have the Blue Mountains, and we have numerous faults and folds in our city area. And the surface geology was pretty well mapped by Mark Ferns and Vicki McConnell, and Ian Maiden contributed a lot to our understanding of the surface geology as well. And so we have a good picture. This is a simplified picture, however. We have the older and younger sedimentary materials. Then we have the Saddle Mountains basalt, a little bit of exposure here and in Adams area. And then Wanapum basalt, Grand Ronde basalt, and beneath the Columbia River basalt group, we have older rocks that we call older Paleogene rocks. And this a little outcrop here along Mackay Creek. So we have good, can you hear the Siamese in the background? So we have good surface geology understanding, and now the challenge is, what does it look like in the subsurface? And that's what this conceptual model and geologic framework and the well cuttings and geophysical logging and all of what we're going to see in the upcoming slides. All right, so with driller well logs, cuttings from the drilling, and geophysical logging with 2005, we have a good set of geologic characterization, you might say. And so we put that to describing the geology in the well cuttings of driller well logs and sorting that out. And doing so, then we could correlate the stratigraphic units in the classic stat diagram, cross-section diagram that I did. And so it started with the stratigraphic columns that were mapped by Mark Ferns. Here we go, where you start at the top of a hill and walk down and collecting cuttings and developing a stratigraphic column. And we have 9 of them on the upper basin. And those were complemented with 13 wells that had cuttings and geophysical logging. And then we correlated that to other wells that had good information that looked like we had strong representation of the geologic units. And this laid the foundation for our subsurface geology and isopachs. And we then correlated those to all the wells that are known to exist on in the upper basin. We have average depth of wells of 200 to 300 feet, and our maximum depth is 1,900 feet. And most of these wells, there's about 1,200 noted here. 850 are on the reservation itself, so we use groundwater. And most of those are domestic use. So, hey, voila! Here's our 3D geologic picture. And for representation in the subsurface, I have 3 sections for A, B, and C. A is North Reservation, the community of Helix. We have 100 feet of sedimentary material, followed by its very, very thin veneer Saddle Mountains basalt, and then Wanapum and Grand Ronde, and beneath that are the older rocks, the Neogen rocks. And then in the mission community on the reservation, we have 40 feet of sedimentary material, Wanapum basalt, Grand Ronde basalt, and older rocks. And up in the Meacham area near the summit, we have mostly Grand Ronde basalts and older rocks. And as you can tell, the older rocks are nearly 5,000 feet beneath the surface and relatively near the surface up in the upper Blue Mountains. Now, an intern had the right idea of looking at the Grand Ronde basalt volume in this block picture and said, if you were to spread it across the entire state of Oregon, it would be 38 feet thick. So there's quite a bit of Grand Ronde basalt in our study area. So from this picture, we are able to look at the aquifers that are supporting the wells on the reservation. So here's a northwest southeast cross section and the geologic units. And excuse me, in the wells in the red area, these red vertical lines, and the dashed black lines are known faults. And so we can see in our well development that we use both Wanapum and Grand Ronde basalts for aquifers, and along the river basin there are a few, very few shallow alluvial aquifers supporting it domestic use. So we're quite proud of this accomplishment here to look at the source waters to our wells. And then so now we have this picture. We complement it with understanding of the other hydrologic components of the conceptual model, the precipitation, the estimated recharge, water use and pumping from the wells. And we also looked at stream gauging, groundwater levels, spring discharge, and the like. I have a whole list of things that we evaluated, but for brevity, I just limited it to these pictures. And pulling it all together, we have a groundwater budget, and resulting with 1.4 million acre feet of water from precipitation, and that includes rain and snow. And then we have a computed recharge using a deep percolation model by the USGS, as I mentioned earlier. We have the outflow from streams, computed evapotranspiration. We have water use, groundwater use, and groundwater outflow from the study area. And each of one of those is computed independently of the other, but when you put it all together, we had a 17% out of balance result, but which is really good considering they're all computed independently of each other. So let's see, looking at this, and we talked about recharge in the shallow and basalt aquifers, we were interested in better understanding the groundwater flow system and the intermixing of aquifers. And this is part of the filling the data gaps. And we took a phased approach, sampling in 2017 and 18, more sampling and data analysis in 2022 this year. And we're working on the analysis and the preliminary results. I say we're mostly Hank Johnson with the Oregon Water Science Center, U.S. Geological Survey. And this work may refine our conceptual model of the upper basin, refine it, meaning we have better understanding of the rock layers and the hydrology and the mixing. So to do this research and sorting, we looked at age dating and mineralization of the waters in the various aquifers and springs. And springs are windows to groundwater discharge, by the way. So in the age dating realm, we have modern recharge, where we used radiocarbon data from chlorofluorocarbons and tritium helium. And the older recharge, the classic carbon-14 age dating techniques, and krypton 85, which is a fairly new method of analysis where you atom trap on. So then we looked at the stable isotopes and general minerals, you know, calcium, magnesium, potassium, bicarbonate, chlorides, and sulfate. So anyway, I might add that each one of those samples was $5,000. So we, in our first year of phased approach, we decided to dedicate all our money, as much as we can, to sampling. And then the second phase, to obtain a grant to do the data analysis, which we are in, thanks to the Bureau of Reclamation. And then the third phase is to analyze the data, thanks to a grant from the Bureau of Indian Affairs. Anyway, sampling was the first 2 years, and we looked at mountains and foothills and valleys, side-by-side wells, shallow and deep, and spring sites, and trying to capture that 3D picture of groundwater movement in the subsurface. And this is a Google Earth image of the various sites that we sampled. And we were able to do 29 wells and 5 springs, and 3 wells with krypton, and numerous wells and springs with general mineral and stable isotopes. And then this year we collected, over the course of a year, 189 isotope samples from precipitation sites in the upper basin and tributaries. We really went all out this year and trying to fill in some of the data gaps. So the intended outcome from this research is to be able to sort the aquifer sources of water, or the well sources of water in the various aquifers, and then evaluate aquifer mixing. And this picture shows 2 identical wells, not identical, but 2 wells drilled to the same depth, intercepting different aquifers. We have the right well here, we have probably a 50-foot seal, and it is tapping as many aquifers as possible, 3 aquifers. And then the left well, we have it sealed all the way down, intercepting only the lowermost aquifer. And in sampling, we will get 2 different ages from these wells. In the first case, we have 2,000-year-old water, parent age, and in the latter case, we have older water, 10,000 years old. And Hank is looking at these, the well construction and the aquifers and the sample results, and sorting out the mixing in these wells. He has models to do this, and a considerable amount of geochemistry, and will be reporting on his findings. Is, I think, going to be totally cool. And the results are basically the springs. We have modern to 16,000-year-old water coming out of the hills. Shallow basalt wells are modern to 20,000 years old. And I must say, in the Grand Ronde basalt in the upper basin, that old water is coming from the very first basalt aquifer tapped. So wondering whether or not it receives recharge is one of those question marks. I wonder if it's a renewable resource. And then we have the deep salt wells, where it ranges from 3,500 to 24,600 years old. This 3,500-year-old water, I know, is a water that receives leakage from above the upper alluvial material. So I do know there's mixing occurring in this well. And in this well, there is very little mixing, and it's probably true to the aquifer tapped. So as I mentioned, a couple of our funding sources for the recent research, but really it started way back 20 years ago, and with assistance with the Administration for Native Americans, the Bureau of Indian Affairs, U.S. Geological Survey, the Forest Service assisted, Oregon Water Resources Department, Department of Geology and Mineral Industries, and the Bureau of Reclamation. And really, when interdisciplinary assessment of water, it really takes a large group of people to do this work, along with the geologic assessments. So a great big thank you to all the people who helped in this work as well. There we go.
All right,
That's it.
Thank you, Kate. Thank you so much. And we have a few minutes for questions. I'm gonna throw to Andrew at about 12:45. So if you have some questions, and you don't have a chance to get them in while we're doing the recording, we stop the recording at 1 o'clock, and then we leave the room open for another half hour. So Kate, if you can stay, there might be some additional questions after the one
Oh, sure.
in the 1 to 1:30 period.
Sure.
But right off the bat, in the minute or two, in the 5 minutes that we have, let's see if I can see people's hands. Randall has his hand up. So Randall, go ahead.
Did I see in your water budget slide that you had a positive 17% inflow minus outflow budget, i.e. the watershed is gaining water every year as opposed to losing like most places?
Oh, I think I should say that it is true. It's a positive extra water. I'd say that it's unaccounted for, not gaining or losing. We just weren't able to account for all the water. It should be a 0% difference, because we're just looking at what's happening to the water in 2010. You know, how much is coming in, how much is going out. There is an assumption of no change in storage. So it's our balance of inflow, outflow. Whoops, we didn't get it all. I suspect there's a lot more in evapotranspiration that was underestimated, and sublimation from snow. So I think there's, an element of
So that
that.
speaks to some of the data gaps you might have.
Right. Thank you.
Okay. Thank you very much.
And I see Paul Shea's got his hand up. Paul, what's your question?
Yes, Kate, would you say something about who the water users are, whether there are like competing uses, or is everybody getting along fine? And how are the stakeholders involved in the study?
Well, thank you for that question. The water users, we basically all get along. I don't know of any lawsuits in the upper Umatilla Basin. There's problems in the lower where there's critical groundwater areas and water level declines. I didn't present any of the data on our groundwater levels, but in 2008, 9, 2012, 2018, and 19, we measured water levels in 200 wells on the reservation and off reservation, and seasonally in the fall and in the spring, to capture the water use and effects of pumping, neighborhood pumping. And what we found is that our groundwater levels in the upper basin are stable. They're recovering, and we also have monitoring wells beginning in 1979 that we measure monthly, and so we can tell that they're stable that way as well. But the stakeholders, the participation from well owners was just great. People were very interested in their water, and by the end of 2019, we were able to give them a little history of the water levels in their wells and whether or not what the changes were. And the stakeholders like Oregon State University, City of Pendleton, all the cities, the Helix, Adams, Athena, Pilot Rock, they were wonderful. They provided data from their wells. And basically the geologic analysis was with Dagami and in the tribes. So there wasn't much involved, and the U.S. Geological Survey, and but mostly Dagami and tribal folks, me, and GIS. So the stakeholders were the homeowners and the agencies. And did I catch anything else? And people really want to know their water, and they're really happy to be involved in this study. So now when we get to computer modeling and looking at impacts from the different types of development, that's going to be a different story, because there will be impacts, and whether or not they're acceptable is on the values of the users, right? So the irrigators are probably saying, well, a little bit of decline's okay because I can get my crops. And, the tribes are going to say it's not okay because it's affecting the springs and our first foods. And the cities will say, well, we'll do aquifer storage and recovery, and, we'll stabilize things that way. So it's, the long-term outcome from computer modeling will generate controversy. But ultimately, it's a decision that will benefit everybody in the basin, because they'll get some security or some understanding of their supply that we all depend on. So anyway, okay, thanks.
Okay, thank you, Kate. Thank you both, Kate and Andrew. We're at our 1 o'clock point, and we like to respect everyone's time and let you go at 1 o'clock, but we keep the room open for another half hour. So if you have a question for either Kate or for Andrew, didn't get a chance to answer it, just to ask, stick around, and we'll be here for another half hour.